So we can now move on with our next speaker. Is as a contributed talk given by Lia GANDER. Is Lia there?
Yes.
Good. So Lia is from l'Università della Svizzera italiana, the Italian university branch in Switzerland, in Lugano. And she will talk on the effect of shape uncertainties on the forward and inverse problem of electrocardiography. And this is a joint work with Professor Rolf Krause, with Michael Multerer, and with Dr. Simone Pezzuto.
Exactly. Thank you for the introduction. So yeah, the forward problem consists of computing the electric potential on the chest given the potential on the pericardium. Instead, the inverse problem consists of reconstructing the potential on the pericardium given some data recorded on the chest. The shape uncertainty is motivated by the fact that typically the shape of the heart is segmented from images, and these images are noisy and have limited resolution, as we can see here in this MRI. Or also here where the slice orientation is more clear. So the shape of the heart is subject to variability and is a source of uncertainty. So having said that, this is our setting. We consider...
Excuse me. We always see the first slide.
Ah, you see the first slide?
Yeah, we are not seeing the presentation. Maybe you have two screens.
No.
No? Okay. So please advance not in presentation mode, but in, let's say, in edit mode, so that we can see slide by slide. Okay.
No.
Okay. Now we see the full screen. Maybe now it's correct. So go on, please.
Okay. Sorry. Thank you for. Okay. So yeah. So you didn't see this slide before, right?
No.
No. We just listened to your comments.
Okay, so yeah, this was the MRI where we can see that the images are noisy and have limited resolution.
Yeah.
So now I introduce our setting. We consider this 2D geometry from the MRI slice. We have that D is the torso, whose boundaries are the pericardium sigma and the chest gamma. The pericardium varies over time and is subject to uncertainty. So we denote here the dependency on time t and on a random parameter omega. This also affects the torso, while we assume that the chest is fixed in time and is not subject to uncertainty. In terms of equations, the potentials U on the pericardium and Y in the whole torso satisfy these equations. We have a zero Laplacian in the torso, a zero boundary condition on the chest, and a Dirichlet boundary condition on the pericardium. And here we are assuming that the conductivity in the torso is constant. To model the shape uncertainty, we consider a reference boundary, a reference pericardium sigma ref, and a random deformation field chi, such that sigma at the pericardium at time t and for the random parameter omega is equal to chi of sigma ref t and omega. And to model chi, we use this Caronello expansion, where this is the expectation function. Lambda k, chi k are the eigenpairs of the integral operator defined by the covariance function. And yk are uncorrelated random variables with normalized variance and with range in the interval -1, 1. Now I present the boundary integral equations to solve the forward problem. Here, I'm no more specifying that the pericardium sigma and the torso D depend on time and omega, but anyway, we have to solve the forward problem and also the inverse problem at each time step and for every sampled omega. So for the forward problem, from Green's identity, we can deduce this formula here for x in the boundary of D, where G is the Green's function for the Laplacian. And this gamma 0 int and gamma 1 int are the Dirichlet and Neumann trace operators that, as we do here, we can restrict to either the boundaries sigma or gamma. And in the same way, we can define the restricted single layer operator like this, that is restricted to the boundary sigma and gamma, and the restricted double layer operator like this. And now with these definitions, we can split the boundary of D in the sigma and gamma component in this formula. And we end up with this Dirichlet to Neumann map. Now, by substituting the given data, that is the Dirichlet data on sigma is U, and the Neumann data on gamma is 0. And by rearranging to have our unknowns on the left side, we get this formulation here. And from this, we can see that we can define an operator A such that the Dirichlet data on gamma are equal to AU, and an operator B such that the Neumann data on sigma are equal to BU. So actually A is the solution operator for the forward problem, and B is the Steklov-Poincaré operator that will be useful in the inverse problem. In practice, we parameterize and discretize the boundaries sigma and gamma. And using Nystrom's method, we can get this discrete formulation of the boundary integral equations. And again, as in the continuous case, we can see that we can define a matrix A such that the discrete Dirichlet data on gamma is equal to AU, and a matrix B such that the discrete Neumann data on sigma is equal to BU, where U are the discrete Dirichlet data on sigma. For the inverse problem, later we will have a continuous formulation with integrals, and to get a discrete formulation for the inverse problems, we will approximate these integrals by means of the trapezoidal rule. And for this, we have to define for both boundaries this diagonal matrix S, whose entries are the surface measures divided by the number of points in the discretization. So now for the inverse problem, the inverse problem is ill-posed, so we have to regularize it. And here we tried several regularizations. So given some noisy data YD on the chest, we have the first regularization is the zero-order Tikhonov, where we minimize the L2 norm of the difference between the potential and the given data on the chest. And we penalize the L2 norm of the potential on the pericardium. By applying the trapezoidal rule, we get this discrete formulation here for this regularization. Instead, in the first order Tikhonov regularization, we penalize the L2 norm of the current on sigma. And again, by applying the trapezoidal rule, we get this discrete formulation. The third regularization is the H1/2 norm regularization, where we penalize the H1/2 norm of the potential on sigma. And this is the discrete formulation obtained again by the trapezoidal rule. Our last regularization is the total variation, where the idea is to penalize the L1 norm of the current on sigma. And but this the L1 norm is non-differentiable, so we typically use this approximation here with beta small. This introduces a nonlinearity in the optimality condition, and To handle this nonlinearity, the idea suggested in this paper by Karui and others is to use the zero-order Tikhonov solution, U0, in the nonlinear term. This approach is equivalent to this formulation here in the continuous setting, where we have this weight term in which the zero-order Tikhonov solution U0 appears. For the discrete formulation, we have to define this diagonal matrix W with whose entries are the weights. And again, by using the trapezoidal rule, we can get this discrete formulation. So now that we can solve the forward and the inverse problem on a fixed geometry, we want to quantify the effect of the shape uncertainty. And to do that, we compute some moments of our quantities of interest. So given the probability space of the random parameter omega, this is the definition of the nth moment of a quantity of interest Q. And in practice, we approximate this integral by a quadrature rule, like, for example, the sparse quadrature or quasi-Monte Carlo. For the sparse quadrature requires the regularity of the quantity of interest with respect to the random parameter omega to converge. So that's why we showed that under usual regularity assumptions, the forward solution is smooth in the parameter space, so that we can use the sparse quadrature for the forward problem. Now I show some numerical experiments. To model the shape uncertainty, we segmented from the MRI the space-time mean pericardium, and we set the covariance of the random deformation field to be the product of a matrix-valued kernel in space and a kernel in time. In particular, for the space component, we used the Matern kernel, and for the time component, we used the sine power kernel based on the geodesic distance theta, so that we took into account the periodicity of the motion of the art. Here, to give an idea of how much we vary the shape, I show the mean, the space-time mean in red, and an example of a deformation of a perturbed boundary in black. And here, the shaded part is the 95% confidence region, whereas the red line is still the mean. Here are our inputs for the forward and inverse problem. These are the forward data. We simply considered a single pulse rotating around the pericardium. And these are the inverse data. For this, we solved the forward problem on the mean geometry, and we added some noise. Since we want to use the sparse quadrature, we first have to numerically test its convergence. And to do this, we compare it to quasi-Monte Carlo. These are the results for the fixed time case and for the first and second moments of our quantities of interest. We can see that we have convergence for the forward solution and for the inverse solution with all the regularizations except the total variation, where these lines are quite flat. So we don't use this regularization for the space-time case. Finally, these are the space-time results computed using the sparse quadrature. Here I show the mean in blue and the standard deviation in red. This is the forward result. We can see that here the standard deviation is small, and it mainly affects the regions with higher amplitude. So this means that in this case, the effect of the shape uncertainty is limited and is smoothed out as the potential propagates in the torso. For the inverse problem, we used the H1/2 norm regularization, and this is the result. here the standard deviation is larger, meaning that the effect of the shape uncertainty is more apparent for the inverse problem. And again, it mainly affects the regions with higher amplitude. To conclude, I would like to point out the fact that the random parameter space is high dimensional due to the space-time modeling. So for this reason, we want to use the sparse quadrature to be able to use a limited number of samples, or smallest possible number of samples in our simulations. And this quadrature requires the regularity of with respect to the random parameter. So we proved, as I said, we proved the parametric regularity of the forward solution, while the analysis of the parametric regularity of the inverse solution is ongoing. In this respect, the total variation regularization seems inadequate for the sparse quadrature due to the lack of smoothness. And this is what we saw from our numerical experiments, but we will further investigate this. And also in terms of more long-term future work, we would like to further investigate the effect of the shape uncertainties by trying to move to the 3D anatomy. So yeah, that's it. Thank you for your attention.
Thank you, Lia, for your talk. Is there any question? One, do you foresee the possibility of accounting for different material properties in the torso in your boundary element software?
Yeah, this is something that we could do. Especially for a piecewise continuous conductivity, this can be done by adding more boundaries. If for a general conductivity, it's probably more complicated. So the first step would be to consider a piecewise constant conductivity.
Thank you. There's a question here, I guess, from Stefano Pagani in the room. So, hello.
So a quick question about, so what do you think, so how to use your pipeline, let's say for a patient? So what do you think that you need to do in order then to apply to a real, let's say, to a patient in a patient-specific setting?
Okay, well, here the idea of the final idea is to for it to be patient-specific, since we segment the shape from the MRI. But of course, this is a 2D model, so this is more for the space-time modeling. Probably for a more clinical application, we would need the 3D anatomy, the 3D case to work. And so, yeah, this is more of a future work.
Okay, and so in that case, you would, let's say that you would have the error coming from your segmentation. And so there are multiple sources of error, and let's say you try to take care about these using your Karhunen-Love expansion, if I get it right.
Yeah, exactly. We get, yeah, we consider, we perturb our segmented boundary to account for errors. And for this perturbation, we need to define a mean and a covariance. And then to model this, we use the Karhunen-Love expansion.
Okay, so there is a question. Thank you.
Thank you.